All right, we have made it to the final unit of AP Chemistry in 2021, getting us to the national exam. And this is going to be looking at chapters 19 and 20 in your textbook. Now, up here in the packet, it did say 16. My apologies, that was a typo. It should say 19. Chapter 19 of the textbook is looking at thermodynamics. And up to this point, we've already talked about one of the three fingers, which is delta H, in Unit 3, which we did way back in probably October, maybe November, is when we talked about enthalpy. And enthalpy is looking at the heat of the reaction, the energy of the reaction. Is it exothermic or endothermic? Well, we're going to focus now on the other two fingers, which is delta S, which is the entropy, and that's what today's lecture is going to be focusing on, which is entropy, delta S, the chaoticness of the system. And delta G takes into account both entropy and enthalpy together, along with other conditions like temperature and pressure. And G, which is called Gibbs free energy, is the thermodynamic quantity that really determines the key question. And the key thing in this unit, the purpose of this chapter is to answer one key question. Is the reaction spontaneous? Or now we say, what you're going to see more likely in the national exam is not the word spontaneous, but instead they use the word thermodynamically favorable. Is the reaction thermodynamically favorable? So under the current conditions, when I mix the chemical reactants, do you expect the reaction by itself, without any external forces, to occur? So if I mix these two chemical compounds together, will we see a precipitate? Okay, if I mix these chemicals together, will they react and form heat? Okay, will we see a color change? Will there be a chemical reaction take place? Sometimes there are, and sometimes there isn't. And Gibbs free energy allows us to look at all the possible variables at the current set of conditions to determine that. So the key thing is we're going to answer, is it thermodynamically favorable? Now in this unit we focus on two things. We look at something that's called a sign convention. A sign convention is where if we know if a reaction is endo or exothermic, positive, negative, is the reaction chaotic, positive or negative? By looking at the signs of these variables, we can predict, will Gibbs free energy be a positive or negative value? We can predict, based on what we know about the substances and their states, if the reaction is thermodynamically favorable before we do any calculations. Or they might ask you to mathematically calculate it. Now, most students love the math because it's plug and chug, and as long as you get the mathematical value right, and more importantly, the sign on the mathematical value correct, that'll tell you if the reaction is thermodynamically favorable. But we can do it estimation-wise too, and that's what the sign convention is. The sign convention is using estimation and conceptual application of the materials, truly know if to predict if the reaction will occur or not. So again, the sign convention predicts if it will occur or not, and then the math really truly determines if it will or will not. Okay? So, spontaneous processes. Reactions that are thermodynamically favorable. And I often use the word spontaneous because it's one word. It's a lot easier to say thermodynamically favorable. But understand that spontaneous means the same thing as thermodynamically favorable. So a spontaneous reaction is one that's going to naturally occur. So an example of that would be if we were to mix together, solutions of silver nitrate and sodium chloride, two aqueous solutions, and we mix them together, we're going to form a precipitate of silver chloride and sodium nitrate. This precipitation reaction occurs very easily at almost any conditions. Here's an example of one. We could mix different chemical reactions, and under the current conditions, they could explode. We could produce a bomb. So under the current set of conditions, will we see a chemical reaction take place? Okay? And we can also look at state changes. For example, will ice melt at room temperature? If I take an ice cube out of the freezer and put it in a cup, Will it melt? The answer is yes. It will melt, therefore it is a spontaneous process. And the reason why, again, is because the temperature of the room is warmer than the melting point of ice, and therefore energy will go into the ice cube, warm it up, and eventually it will melt it. But if you have an ice cube and you put it outside on a good old Wisconsin day at negative 25 degrees Celsius, it's not going to melt. It's going to stay frozen. So again, we have to look at all the different variables, and that's where Gibbs free energy will come into play in our second lecture of this week. Now, we've already talked about two key factors. We've already talked about the first, which is enthalpy. Typically speaking, reactions that are exothermic tend to be spontaneous on nature, because in an endothermic process, energy has to keep coming into the system. Energy has to keep being provided to sustain the reaction. And therefore, if the reaction is not hot enough, most of these reactions won't occur, specifically at room temperature. And the focus of the national exam usually is looking at reactions that occur at room temperature, more importantly at 25 degrees Celsius. 25 degrees Celsius is considered to be standard temperature for thermodynamics, not 0 degrees Celsius for gas laws. For thermodynamics, it's 25 degrees Celsius. So at 25 degrees Celsius, which is about 80 degrees Fahrenheit, okay, a lot of these processes won't occur unless they're very, very, very warm. So exothermic reactions tend to be more self-serving and self-sustaining. Again, if it's exothermic, it's going to have, the delta H value is going to have a negative number. Negative means it's exothermic, that energy is released to the surroundings, which makes it exothermic. Or the other key sign convention is it's less than 0. Make sure you understand both of these concepts in determining sign conventions. So a negative or delta H is less than 0 indicates an exothermic reaction, which tends to be thermodynamically favorable. Entropy is the focus of today's lecture, and entropy is looking at the randomness or the orderedness of the system. The more chaotic a system, the more chaotic it is, the more entropy it has. And based on the universe, this is favorable. The universe favors chaos. This is called chaos theory for those of you that might want to go into a physics degree. The universe favors chaotic systems. We as humans prefer ordered systems. We want things orderly. We want to be able to control temperatures of a room and not be in negative 25 degrees Celsius outside. We want to create favorable systems. But in return, to create systems that are very ordered, we have to expel enormous amounts of energy to do so. But the more chaotic a system is, the more entropy is, and the more favorable is. So that's the key thing. So for in this unit, if there is an increase in entropy, or if the delta S value, the entropy of the system, if it's a positive number or greater than 0, this means or implies that according to entropy that it is favorable. The more chaotic it is, the more favorable it is in regards to thermodynamics. Let's turn the page. All right, so the more random or disorder a system, the greater the entropy and the more favorable it is. Okay, so there's certain variables to look at. One is states of matter. What state of matter do you think has the least chaos, or is the most ordered state? Where do we have the least chaos or the least entropy? Hopefully you're thinking to yourself, the solid state. The solid state has got the least chaos towards it. Which state has got the most entropy or the most chaos or the least order? What system has got the most, what state of matter has the most randomness to it? And hopefully you're thinking gas. Liquids and aqueous ions are about the same, and they fit kind of in the middle. So one thing to consider is the state of matter. If you look at the chemical reaction, if you look at the states of the substances, the more gas you have, the more chaotic the system and the more favorable it is. So if on the product side there's more gas present than on the reactant side, we have a more chaotic system, which is favorable for thermodynamics. If there's less gas and there's more solids, then it's less thermodynamically favorable when it comes to the state of matter. There's also things called microstates, and this is kind of getting into a little more higher in physics, but when we look at states of matter, there's three basic types of movements. One is vibrational. When we have a chemical substance that maybe it's a bond, these things tend to vibrate. They tend to wiggle back and forth. Well, what affects the amount of vibration a chemical compound has? Well, one of them is temperature. What happens to molecules when we increase their temperature? They vibrate more. Those vibrates intensify. Well, that's increasing the amount of microstates in a compound because its vibrating state is a greater one. In a solid, things can only vibrate, so they only have one of the three types of movements of particles. When we get into a gas, gas particles can also rotate, so these things can twist and turn around into different 3D circles and rotate just like the Earth rotates. Rotational movement is another microstate of movement. And lastly, there's translational, which is this gas particle moving in a linear path until it bounces off a wall or something. That too. And as temperature increases, things will rotate faster. They will move in a translational or linear line faster. That's increasing the number or the degree of the microstates as well. So when we're looking at systems, we're looking at all these different variables. Is the products got more chaos, more entropy with it, or is there more order with the products compared to the reactants? If there is more, then it is entropy favorable. Okay, so real quickly, for 1, 2, 3, and 4, I would like you to go ahead and predict if you think the entropy of these systems are increasing or decreasing when it comes to the amount of entropy in the system. All right, so if we're going from the solid state to the liquid state, if we are, I just made a mistake there on that one. If I'm going from the solid state to the liquid state, I am increasing the amount of entropy because there's less order in the liquid state because the particles have more freedom to move. Along with just being able to vibrate, now they're able to actually rotate and also move in translational directions, and that causes an increase in the number of microstates, and therefore there's more chaos in the liquid state than solid state. That also increases going from the liquid to gas state. Increase in temperature also increases the entropy of a system because it increases the degree. It vibrates more. It moves at a higher rate of speed. There's more chaos with it. As I've already said, if there's an increase in the number of moles of gas in the chemical reaction, there will be an increase in the entropy of the chemical reaction. Therefore, it is thermodynamically favorable. The second law of thermodynamics is right here, this next statement. The entropy of a completely ordered pure crystalline solid at 0K, absolute zero, is 0. Almost everything has entropy, and since absolute zero is a theoretical absolute, probably not able to be attained, everything has entropy. When we do enthalpy problems, anything that was an element, its enthalpy value was 0. But for entropy, when you look at the thermodynamic tables that I'm going to give you and provide to you, thermodynamically speaking, they will have values associated with all of them. All right, and therefore, when you look them up in the table of thermodynamics, it won't be 0, it'll be something other than 0. All right. So again, I'm going to pause the lecture, and I want you to think about the next 3 examples, and I would like you to predict: do you think this is an increase in entropy or a decrease in entropy based on what we see here from the chemical substances? All right, for the first one, the dry ice, it is going to go from a solid state to a gaseous state when we take it out of the freezer. Again, there's also an increase in temperature. Both of these signify that there will be an increase in entropy of the system. B, the reason why there's an increase in the entropy is we go from a pure substance to a mixture. When we go from a pure substance to a mixture, there's more chaos, there's less order because there are the different interactions between the substances. Now, along with having the intermolecular forces between the pure substances, now we have intermolecular forces between solute and solute particles, solute and solvent particles, and solvent and solvent particles. There are more microstates because it's a mixture, and there's much more variability and randomness to a mixture than there are pure substances. Therefore, there's an increase in the entropy. And C, we're going from the gaseous state to liquid state, so that's a decrease in entropy. So of all of them we've seen so far, this is the first one where we would say that it would not be thermodynamically favorable because we're going to a more ordered system, and therefore it is not thermodynamically favorable. Okay? Now, the next page, we're going to look at the mathematics of this. So this is predicting the signs, and that's what your homework in Pearson is going to focus in more on, is going to be just doing the conceptual applications of being able to predict if the reaction is thermodynamically favorable or not according to entropy. Okay? But I also want to focus now on looking at the tables in Canvas along with the this packet. The next thing you'll find is the tables of thermodynamically values. If I turn the page, all right. So, how do we calculate the mathematical entropy of a system versus predicting it? We find and look up the table of those entropy values, and just like back in Unit 3, when we did products minus reactants for enthalpy, we're going to do the same thing for entropy, but now just using the delta S values. All right, and the first thing to be able to do this, we must know the balanced equation. All right, because just like in enthalpy, we need to know the coefficients because we'll multiply the substances by the coefficients if they're not a 1. So we have to take into account the number of moles of substances to be able to accurately get the entropy or enthalpy of the system. All right, so calcium carbonate is CaCO3, and it is a solid. Now, how do I know that? Calcium carbonate is an ionic compound. And again, all these reactions are going to be assumed to occur at 25 degrees Celsius, which is just a little bit warmer than room temperature. So if it's got an ionic bond to it, if it begins with a metal, it's going to be a solid at room temperature. Okay, it's going to decompose into, can you remember what carbonates decompose into? Calcium oxides, which again is an ionic compound, solid, and carbon dioxide gas. Now, if you were asked to predict, if I asked you to predict the sign on the entropy, would you expect it to be a greater than 0, a positive number, or negative value less than 0? What do you expect? Hopefully you're saying greater than 0, or you would predict that the entropy of the system would have a positive value. There's going to be increase in entropy because a couple variables. First of all, we have 0 gas on the left, and we have gas on the right. So we're forming a gas which is thermodynamically favorable. It's more chaotic. It's more entropy. Secondly, we have 2 substances produced versus 1. We have 2 different materials, a mixture of substances, and that too has got a more randomness to it, which causes a more or a larger entropy value. So already going into it, I expect the value of delta S to be a positive number. All right, so how do we actually calculate it? The first thing we do is we look up the entropy values of the products. Okay, oops, that was my bad. That was the calcium carbonate. That needs to be the reactant. That should be on the that side, my fault. So let me erase this here. So I should have been looking up plus the carbon. And I forgot to mention this reaction is balanced. I kind of skipped that because I know it's balanced ahead of time, but we do want to make sure that the chemical reaction is balanced. So we add up the reactants since all of them have a 1 as a coefficient. All right, that's pretty simple to do. We just have to look up the values. So we add up the two products minus the reactants, plug that into our calculator. And we get 0.1605 kilojoules per mole Kelvin. Now, one thing I do want to point out, on the national exam, they are notorious for giving delta S values that are not in kilojoules per mole. They tend to be in joules per mole, and that'll be more important later on. So do be cognizant and aware of the signs. This table that I've given you is in kilojoules per mole. That way they're all in kilojoules, but do be aware if it's in joules, and that'll be more important next time we talk when we look at Gibbs free energy, because all of them have to have the same units in order for them to be able to be mathematically added or subtracted together. All right, so let's drop down to number 3. Iron 3 oxide is reduced by hydrogen to form iron metal and water. Real quickly, pause the lecture and balance this chemical reaction. All right, the balanced equation there, iron 3 oxide is Fe2O3 plus hydrogen, H2. Hydrogen is a diatomic element. Iron is not, Fe. And then water in the gaseous state, and then there are the coefficients. All right. Now I forgot to mention in problem number 1 that we did end up getting an S value, an entropy value of 0.1605, which is a positive quantity. We did predict that it was going to be greater than 0, which it is, and therefore there is an increase in entropy. And at first people think that's kind of small, but if this was in joules per mole, it'd be 160.5 joules per mole Kelvin. And that's why a lot of times they do put in joules per mole versus kilojoules to still understand that it is an important mathematical value, and it is a positive one. All right, so now real quickly, use that table of entropy values that's in Canvas. I would strongly recommend that if you're virtual that you do print that off. You have access to it so you can do these problems a lot easier than flipping back and forth like I'm going to do here in a second. But go ahead and do the mathematical problems and see if you can get the right answer when you restart the lecture. All right, doing the mathematics, and hopefully I did it right myself. Again, make sure products always come first in all of these equations when it comes to the change in entropy or enthalpy of a system. So this one would be much harder to predict the sign of because we have 3 molecules of gas and 3 molecules of gas. The only thing that would be a little bit different is the fact that we have 4 moles going to 5 moles of substances. So since there's more moles of chemical products, that probably does tend to predict more on the side of it being an increase in the entropy of the system. And that's exactly what we get here. We get a positive entropy of 0.1415 kilojoules per mole Kelvin. So that's how we can mathematically predict and also do sign conventions, which is the focus. The focus of the homework in Pearson is to mainly look at the chemical reactions and processes and states and be able to predict if the sign of the entropy will be positive or negative. Okay? Now, a couple other things. As I said before, if a reaction is endothermic, typically it is not spontaneous. It is not favorable, which means it's not likely to occur. But we can take a reaction that's endothermic and make it favorable. For example, the ice melting. Ice melting is an endothermic process. How can I get ice to melt spontaneously or just the way that it will occur naturally? And the key question is if the temperature is above 0 degrees Celsius, because that's the melting point of ice. So even if a reaction is endothermic, we can cause it to be thermodynamically favorable at higher temperatures. Now, why is that? Because there's a second variable to consider, which ends up being, okay, delta S, which is entropy. Even though ice melting is not favorable, it's not favorable in terms of enthalpy, the heat of the reaction. It is favorable because we are going from a solid to a liquid. And that is favorable when it comes to entropy. So now the next lecture is going to look at when we have two countering variables to consider, what can we do to look at that to examine if the reaction will be spontaneous or not? Will it occur? If they're both favorable, then the reaction is more than likely going to occur, no matter what probably the temperature is. If they're both not favorable, then they're likely not to occur no matter what temperature as well. But if there are countering viewpoints here, if it is favorable in one and not favorable in the other, temperature plays a key role in determining if that reaction will occur or not. And that's what the next lecture will focus in on Gibbs free energy. So that's entropy. Entropy is looking at the chaoticness of the system, and the states of matter are critical to analyze, and the number of moles of each of those states is very important to look at. And once you look at those, ask yourself, is the products got more chaos or less chaos than the reactants to make sign convention predictions, or mathematically, we now know the equation which is on the green sheet for us to be able to mathematically calculate the entropy of it and understand if it's positive, there's an increase in entropy, which means it's favorable. If it's negative, it is not favorable. All right, so now I'll go to Pearson and do the homework on these problems. Most of them are multiple choice. Short answer, you should be able to breeze through it very quickly and just to see how well you're understanding entropy and these concepts. Okay, again, thanks for listening. Problems. So going to the table 2 oxide. Here is an example of the thermodynamically table that I'm talking about that's in Canvas. The first column is delta H, which is the enthalpy of the substance. So the top one here is silver solid. We can see because it's an element, the enthalpy for it is 0 if you think back way back to Unit 3. And the units on this, it's hard to see, are kilojoules per mole. The next column is delta S, which is in kilojoules per mole Kelvin. Now, entropy is a little bit different in the fact that Kelvin is associated with the units for it, because entropy does change as temperature changes. And then there's delta G, which is Gibbs free energy, which will be the second lecture later on this week, and that too has got the same units as H, kilojoules per mole. Okay, so that's what the tables are when we look at how to do the mathematics of these concepts. So again, the first one is always delta H, delta S, and delta G. And don't forget that the entropy has got the units with Kelvin associated with it. And sometimes that is very important when it comes to the national exam. So I'm going to be referencing this table as we go through these mathematics. We're going to go ahead and find calcium carbonate. And I'm trying to find it right now. Okay, calcium carbonate. The second column is the S, 0.0929. 0.09. The calcium oxide first, products are first, 0.0398. And carbon dioxide gas is 0.2136.